In this presentation, I'm going to take you through some of the background and progress on research for GC 2.1, which is concerned with the soft magnetic materials used in electrical machines. To give you a bit of background, this grand challenge is focused on the manufacturing aspects of soft magnetic cores. Particular interest initially is looking at the effect that different manufacturing processes have on the subsequent properties of the materials in service. Particularly interested in core loss on two aspects. The effect that stress is applied during manufacture to the bulk of the core have, so this is things like shrink fitting, tolerancing of mechanical fits and the like. And the second one is the effect of the process used to blank out the laminations, whether that's stamping or laser cutting or wire erosion. All of those have varying effects on the cut edge in terms of degrading the magnetic properties in the vicinity of that cut edge. I think what we're really trying to do, if you wanted to summarize it, is to try and get a systematic and scientific understanding of build factor. So that's the factor that's often introduced in design and manufacture to slightly derate the magnetic properties that you expect in a final machine product. So you take the manufacturer's catalog data, you derate that slightly when you make your predictions of what your actual machine will produce by way of loss. That's usually empirical, it's usually gained within particular organizations over periods of time, and really what we're trying to do is to get a good understanding of what contributes to the need for that build factor, and therefore what remedial action might you be able to take to minimize the amount of degradation you have to build into your design. The initial focus of this grand challenge is on cobalt iron. It's not exclusively cobalt iron, but it's principally on cobalt iron for two reasons. Firstly, there's very little published literature compared to silicon iron. Degradation of cut edges and effects of stress on the loss in silicon iron is fairly well documented, generally in terms of lots of characterization of material properties and not necessarily the full chain through from how that impacts on loss in an actual machine, although there is some of that. So relatively little cobalt iron data, but also that cobalt iron is a key material in very high performance machines, which is the kind of focus of our hub. So what we're starting to do in the initial phases is to concentrate on cobalt iron. If we look at the effect of compressive stress on loss in cobalt iron, as I've said in the previous slide, there isn't an enormous amount of data out there in the public domain, but what little there is does show that cobalt iron has a strong stress dependency, and that the nature of that stress dependency, if not necessarily the magnitude of that stress dependency, is very typical of what is seen in silicon iron. In other words, we get a small reduction in loss with a modest amount of tensile stress, and then it picks up, but we get very significant increases in loss as we apply compressive stress. So here's various bits of data. The one on the left is some results provided by Thomas in 1980 on a cobalt iron vanadium alloy, and what you see is for relatively modest levels of stress we get significant increases in loss. In this case, about a 60% increase in loss for 100 megapascal of compressive stress. So the key thing is, where on that stress curve do we sit when we apply different processes? This particular data is at quite a high frequency. It's 400 Hertz, 1.8 Tesla, which is a very typical point for aerospace kind of generator work characterization. Thornburg did some work in the late 70s, some elegant work looking at applying shrink-fitted sleeves onto toroidal samples and characterizing those at different levels of pre-compression, and again showing quite strong stress dependencies at different operating points in magnetic terms for different levels of stress. And again, the problems come with significant compressive stress. More recent work in a lengthy report published by the Air Force Research Laboratories shows again very significant increase in loss in compressive stress. This isn't directly comparable data because this is applying the stress orthogonal to the direction of the field variation, but nevertheless reaffirms the view that even though there isn't a lot of data out there, what is out there is indicating some stress dependency that we need to understand. clearly characterizing material and showing that at a particular operating point there is an increase in loss with stress is in itself quite useful information, but ultimately what we want to do is to connect that chain up from the manufacturing process to the in-service performance. And essentially what we're trying to do is improve the loss predictions that take account of manufacturing processes in 3 steps really. The first one is probably the critical one, which there isn't a lot of information out there, is to establish the stress levels we are likely to encounter during manufacturing, okay, through things like interference, fit of the casing, through the tolerancing of interference fits and so on, through mismatches in thermal expansion. What are we likely to see by way of stress levels? We then need some material data, characterization, this is the same graph as was in the previous slide, to tell us how we adjust the loss coefficients that we use in our loss model to account for stress and potentially other factors such as temperature as well. And so we have a material based piece in the middle, which is taking the stress distribution locally within each element of our finite element model, modifying the loss coefficients for that element, and then using a post-processing tool, which is a slightly custom built tool that takes time varying flux density waveforms from electromagnetic finite elements analysis, predicts the loss with coefficients that have been individually corrected for stress. So you can see it's quite a data handling process in terms of having different coefficients in different elements of the stator core depending on the stress to which it's exposed. The efforts on this kind of process of putting all this together in the past 8 months has naturally been focused on the modelling aspects. There is an enormous piece of work to do in the middle around the material characterization, but the limitations on laboratory access since March has meant that the focus over the recent months has very much been on the modelling, in particular the mechanical modelling, but also some of the data handling of putting together finite element data from stress through a characterization tool using some primitive data from collected externally through to loss coefficient maps. So if we look at the mechanical modelling, the first thing to do is to get an idea of the likely stress levels we're going to see. So we initially focused on compressive stresses from either the shrink fitting of the casing, thermal expansion mismatch, or some tolerancing issues. So you might, for example, get thermal mismatch between the core and the casing. Generally, if it's an aluminium casing, the aluminium will expand more than the core, but if you were looking at things like composite casings or materials with lower coefficients of thermal expansion than the core, you might get some additional compressive stress during operation. But what we're principally focused on are the effects in manufacturing. So this is what is the tolerance to which those components are made, and what is the effect of the common practice of shrink fitting a casing on. So in machine manufacturing, it's very common to shrink fit the casing onto the laminated core in order to get good thermal heat transfer across that core. The level of interference will clearly affect the level of hoop stress that we build up in the back iron of the core, and what we're trying to do in the initial modelling is understand what orders of magnitude of stress are we likely to have, and therefore what likely orders of magnitude of change in core loss will we see. So here's some data taken for a 200mm diameter stator core, which is going to be shrink fitted into an aluminium housing with a 0.1mm lamination, 0.1mm interference fit. There are analytical models for shrinking of 2 cylindrical sleeves. Obviously the representation of the core here is really simplified to the back iron, which, as we'll see later on, is a pretty good assumption for most geometries of machine. And we can see the typical analysis for this particular casing. I think it's a 10mm thick casing, shrink fitted onto the core is about 35 megapascal of hoop stress in this simple analytical model at the inner edge of that cylindrical representation of the core. So we're talking in the several tens of megapascal for a 0.1mm radial interference or a 0.2mm diametrical interference. So when you think about the kind of interferences that we might use or the kind of tolerances we can control on those interference fits, we're probably looking at stresses in the orders of a few tens of megapascal, which, as we saw from the earlier data, is starting to give us some appreciable increase in loss. We then progressed that work from analytical, looking at various models in two-dimensional finite element analysis, various fidelity of models. So we've gone for a finite element representation of a shrink-fitted aluminium. We've looked at doing it through simple contact pressure onto the very simple representation of the back iron as a plain cylinder, which both validates against the analytical but also gives us some idea of what the effect of adding more and more features into our mechanical model, whether there's any value in that. You'll see two finite element plots on the right hand side. The first one is for a full representation of the baseline stator core model that we're using, and you can see for that same 0.1 diametrical interference, you can see a significant stress in the back iron and relatively little in the teeth. And as we'd expect, the teeth do stiffen up a little bit of the back iron, particularly just adjacent to the tooth. But in general, the stress levels we see aren't greatly higher than in a simple ring model, other than very localized stresses in the corner. It's probably worth pointing out, of course, that in this model, none of these stresses are anywhere near being problematic in terms of the yield of the lamination. So we're not really so concerned about stress concentrations, providing that at this kind of level of a few tens of megapascal or even up to 100 megapascal is not problematic from a mechanical perspective, and actually won't have a big effect on the core loss change because of the weighting is small for that very tiny region of the core. So we're more interested in what is the change in the bulk stress or the weighted effect on the iron loss. The diagram at the bottom right hand corner is another level of fidelity in which we've added in some conductors. In this case, these are some hollow copper conductors that you can hear more about in the presentation of Grand Challenge 2.2. So this is just showing some level of stiffening up of that structure, some reduction in the back iron hoop stress as a result of stiffening up the remainder of the stator core. But not too much, largely has an effect on some of the localized stresses. So you can see that a simple hoop model of the back iron gets you reasonably close, although there is some value in terms of getting a more accurate picture by representing the whole geometry mechanically. This is some data we have on the various properties, including some consideration of the slot liner being done with a rigid material, and that just gives you some properties for the half tooth. If we look at the histogram of stress levels we encounter, if we model without the tooth or with the tooth now, at first glance these histograms look very different, but when you look at the scale on the left hand one, it's a very narrow scale. So we've got a distribution of stresses from the outside to the inside of that simple ring model of the back iron, centered around about 34 megapascal, with some spread a little bit, as we'd naturally expect, spread towards the inner edge, as you would expect in the analytical model as well. With the tooth, the histogram, we can see the bulk of it is again sat in that same window there. The reason we've done a histogram is to show, even though there are some outliers of stress around the corners, the bulk of that stress is pretty close to the stress levels we predict without the teeth, with an average stress in the stator back iron region of 33 megapascal. So as we'd expect to see, including the tooth gives us a little bit of localized stiffening of the structure around the base of the tooth, which slightly alleviates the hoop stress that we see. If we add in the windings, we see, so that's the same kind of stress as we had before on the left hand side. We can see again some increase in the windings. This, of course, with the teeth involved, we have a large section here in the main tooth body exposed to minimal stress, so sitting in the 0 to 10 megapascal range. So what we're seeing is there is value in having a high fidelity model of the mechanical stresses, but you're not going to be too far off in terms of understanding the stress levels from simple analytical and cylindrical models. We've taken that a little bit further in terms of the results I've presented so far have just been for one level of interference, and we've tried to look at the effect on stress levels of both the level of interference in microns along the one axis and the aluminium housing thickness in the other axis. And again, because we've got this weighted contribution to the overall loss from these stress levels, neither the maximum or the average is a good measure, but if we look at the maximum stresses, which tend to be very concentrated and not having a big impact on the on the losses, we have very high stress levels for very thick casings with very high levels of interference. No real surprise there. If we look at the mean von Mises stress map, which again isn't a perfect measure because there's a non-linearity between the stress and the increase in loss, there's then a volume weighting of how much volume contributes. But basically we can see we're generally going to be dealing with less than 100 megapascal, even for very thick housings with quite high levels of interference. But the dependency on housing thickness, there is a certain non-linearity. Another feature, if you go to an even higher fidelity model and start looking at 3D modelling, is the fact that the previous 2D FE models were very much looking at stress within a plane, assuming essentially an infinite stack length. And this is a 3D model that's accounting both for the laminated structure of the core. In this particular model, it's just a simple model of the back iron, and a model of the casing in which the casing extends beyond the core. So very common in electrical machines for the casing to be longer than the stack in order to accommodate the end windings, and yet you may or may not take the time to shrink that to profile the inner bore of that casing. But in this case we've got a plain bore to that casing, so there's an interference fit, and as you'd imagine, the part of the casing that's unconstrained by the stator core will shrink in a little bit more due to the interference that we apply during heat shrinking. And so what we get is a stress concentration near the end of the lamination stack, which more or less doubles the compressive stress towards the end of the stator stack. So again, in terms of overall loss, you have to bear in mind the weighting that this highly stressed region will have on the overall loss. But in terms of localized loss density, we wouldn't be surprised to see an increasing loss in the end laminations if we have an overhanging case that's been shrink fitted because of this tendency to stress concentrate near the end. That's slightly worrying because obviously it's also the end laminations that will take the end winding flux, the incident flux that's hitting the laminations, if you like, in the wrong direction, hitting them face on. So electromagnetically we'd expect extra loss in the last few end laminations from the end windings. We're also compounding that now by having a stress concentration. So this may start to influence how you design your casing, and if you are going to put a heat shrink in, whether you heat shrink the entire case or only an insert that sits around the finishes at the end of the stack. But so some three-dimensional effects as well. What we're doing at the moment is we've put together a detailed material testing plan in consultation with Carpenter, who've been kind enough to supply us with some Hyperco 50 material for the testing. And so we've put a series of 25 experimental tests. These are both done on an Epstein frame and on a single sheet tester, in which the rig for the single sheet tester has been modified or being modified to allow stress to be applied. We're also preparing some samples with varying numbers of cuts in the Epstein frame sample, done with different cutting techniques, so laser cutting, some stamping and the like, and looking at the effect of progressively more cuts within an Epstein frame as a means of quantifying in a fairly precise way the effect of additional edge losses in samples. So this is a program that's been put together. We've specified the sample requirements, the condition and the precedence of those samples, and that's a package of work that's coming together and will accelerate as we gain full access back to the laboratories in the coming months. Just on the measurement rig, we're putting together a rig using a combination of our in-house capability for loss measurements, using a laboratorio electrophysica equipment that we have, in combination with a low-cost universal tester shown on the right and a single sheet strip tester shown on the left. So this is a rig that we're in the final stages of designing, and we'll again start to assemble and put together when we return to the laboratories full pace. Something on the short-term future plans is to complete the build of the test rig. Those parts are being specified up, and some of the challenging bits, such as stopping the laminations buckling when we apply compressive stress, is ongoing. To complete the test program, including quite a bit of sample processing using capabilities you can hear about in WorkPack GC 2.3, and then to put the entire prediction process together for a cobalt ion machine and validate the findings on a demonstrator machine. So that's a very quick gallop through the background, the work we're ongoing, and what our future plans is. As I say, of all the grand challenges perhaps in the hub, this is the one where we've really have hit a bit of a bottleneck with laboratory access over the summer in particular. We're starting to remedy that now and bring the experimental part up more in balance with the modelling work that's been done. I hope you find that informative, and hopefully you can start to see where it fits into the wider picture of hub activities. And thank you very much.